Hello everybody. Today my lesson is about calculus, chain rule, physics, and I will give you examples. Okay. The example here is here is the ground. So you have a ball. The ball has a mass m. You just drop the ball. You drop it. Drop it. Drop means the velocity at the beginning is 0. So initial velocity is 0. You drop it. And then it goes down. Say after a while the ball is here. Of course, when the ball is here, the ball has a velocity going down, right? It's no longer 0. It's no longer 0. Here it has a velocity. And it continues dropping until it hits the ground. So what do we want to find? What is the velocity when it hits the ground? To say exactly, we say just before hitting the ground. What is the velocity just before hitting the ground? So what is the velocity here? So we can call this velocity final velocity. This is initial velocity, which is 0 because you drop it. The final velocity, of course, is not 0. It's the velocity just before hitting the ground. We all know that after it hits the ground, the ball is sitting on the ground and not moving, the velocity is 0. So the velocity we want to find is just before hitting the ground. Let's call the distance moved from the initial position to somewhere here. Let's call this distance S. This distance, let's call it S. Okay. The ball is falling down. This kind of motion, in physics, we call it free fall. Free fall. When a body is dropping by itself, free fall, it moves faster and faster. That means there is an acceleration. What is the acceleration? In physics, in experimental physics, we found the acceleration has a value 9.81. Meter per second square. This number is a constant. So that's what we found from experiments. This acceleration has a name. We call it acceleration due to gravity. Because the ground is the Earth, Earth is the big body. The Earth and this mass m, they attract each other. The first is so big, We don't see the Earth is moving, but we see clearly the mass m is falling down. So acceleration is a constant. In physics, what is acceleration? So we have a definition. The acceleration is the rate of change of velocity. Acceleration is the rate of change of velocity. All right. How do we write rate of change of velocity? Here is calculus. So the label for rate of change of velocity is the derivative of velocity. Rate of change in calculus we call the derivative. This is prime notation. We put a prime, which means the derivative. There is another notation. dv by dt. So this is another notation now. This label, this fraction line, we do not pronounce dv over dt. No, we do not pronounce like that. We say dv by dt. Okay, so this fraction line we pronounce by dv by dt. And this label has a name. It's called okay, no. This label is called a Leibniz notation. Notice that this is called notation. And usually in the textbook, calculus textbook, the book will say that this notation is not regarded as a ratio. You do not consider this as a ratio. But some book, calculus book, also has a remark, for the time being. For the time being, it is not considered as a ratio. For the time being means temporary. For now, we do not consider it as a ratio. But later on, we may consider it as a ratio. It's just for the time being, all right? Because this is a notation. However, later on, we found consider it as a ratio is very convenient. It's very instructive. Okay. So let's go on. This acceleration A by definition is dv by dt, and the value is 9.821. and it is a constant. Now, we consider this as a ratio. Okay, let's give you an example of a ratio. All right. 5/7. This is a ratio. I can multiply the ratio by 1. It doesn't change anything. I multiply it by 1. So what is 1? I write my 1 in a special way. 6 times 6. Or 6 divided by 6. This is 1, right? So 5/7 multiplied by 1, you don't change anything. But then this trick is that I rewrite this. 5/6 5/6 times 6/7. Now these are ratios so that I can do that. You see that 6 and 6 cancels? So the result is exactly 5/7. So this is because we consider this a ratio, because it is a ratio. Now we consider this as a ratio. Now the trick comes. Let's write dv by dt multiply dv dt. And I put something here, put something here, because I consider this as a ratio. So I put ds, ds. ds and ds cancels. So my result is still dv by dt. What is s? S is distance. And here is the distance. S is the distance the ball moves. S is the distance. Why we do not use d to represent distance? If we use d to represent distance, I have dd by dt. It's a little awkward. dd, it's a little awkward. So in physics, we usually use s to represent the distance. ds by dt is the rate of change of distance. What is the rate of change of distance? It's the velocity, is it? How fast you are moving. In 5 minutes, the distance you walked maybe 50 feet or 50 whatever, 50 meter. So the 50 meter divided by 5 minutes is called as a velocity, right? So this is v. Okay, now let's see now. dv by dt is a acceleration. Acceleration is this, and this can be written like this, but this is v. Therefore, acceleration is v dv by ds. So I need some space. So acceleration is v dv by ds. Do you follow? This is v, acceleration is v times dv by ds. So it's this. And then this is equal to 9.81. It's constant. Acceleration is a constant. Now, we can do calculus now. Okay, v dv by ds is 9.81. This is the derivative. But this is also a ratio. So I multiply the left side by ds. I multiply the right side by ds. What do we have? So we have this now. v dv equals 9.81 ds. Because I consider it as a ratio. Once I have this, I integrate both sides. What is this? Use power rule. So this is what is this? This is a constant. You can move the constant before the integration. The d and the integration cancels. So the result is just s. So the integration of ds is just s. But don't forget, when you do integration, you have an integration constant, or constant of integration. So you plus c now. How do we find c? We apply some conditions. What is the condition here in this example? When the distance moved is 0, that means at the very beginning, it hasn't moved at all. So the distance moved is 0. But at the very beginning, what is the velocity? 0, because we consider this case. At the very beginning, velocity is 0. So when s is 0, v is 0, which means c is 0, right? Okay. S equals 0, then v is 0. When s is 0, v, we call it initial velocity. The initial velocity is 0, which means c is 0. You follow? At the very beginning, the mass m has not moved at all, and the initial velocity is 0. 0 here, 0 here, c is 0. Therefore, I can rewrite this with c equal to 0. So, I rewrite this. Okay. So this is my result. the constant of integration is 0. So this is, and back to the initial example. We want to find the final velocity. I want final velocity. What is the distance moved if the velocity is here? So the distance moved is, it drops to this place, right? So it moves this distance. So let's call this distance height. H is the height of the ball when time is 0, initially. Yeah, initially. When S becomes H, the V is V final. So I have this now. I have V final. Okay, I can use this. So V final, well, maybe I should rewrite it. V final square divided by 2 is equal to 9.81. S is H. Okay, this is what I found. And using this, you can find the final velocity if the H is given. Let's do another trick. Let's multiply this equation by the mass to the both left-hand side and right-hand side. So I multiply mass. Okay. The mass of the ball is m. So I multiply mass here, I multiply mass here. Do you see something? 1/2 mv squared. What's that? It's kinetic energy. What's this? M, acceleration, height. This acceleration has another label, it's called a g. G is acceleration due to gravity. So this is mgh. What is mgh? Potential energy. Kinetic energy is equal to the potential energy. What's that? Conservation of energy. Conservation of energy. When the ball is here, it's not moving, initial velocity 0. Because of the height, this ball has potential energy. When it drops, say here, the potential energy is less because the height is less than h. Potential energy is less. But it has the velocity here. So potential energy becomes less and the kinetic energy created. At the beginning, there is no kinetic energy because velocity is 0. When it drops, potential energy decreases, kinetic energy increases. When it hits the ground here, because we measure potential energy from the ground level, so when it hits here, all the potential energy is gone and potential energy is converted to kinetic energy. So this is conservation of energy. So that's what the result tells you. Okay, that's this example. Now I'm going to extend this example. Okay. How do I extend this example? All right. Okay, so let me erase this. The extent is this. This is the Earth. And my ball is very high up. Here. My ball is here. Imagine you can fly up very high and you grab a ball, and how high you are, it's the radius of Earth, I call it capital R. So you are at one radius of Earth up. So this is also R. So this is an extension of this. The H above the ground is the radius of Earth. So this is the ground. This is the ground. How high is the ball? It's the radius of the Earth. And you drop it. The velocity is 0. You drop it. Just like this. You drop it. What is the velocity when it hits the ground? Just before hitting the ground. What is the velocity here now? It drops. So what is the velocity final here? No, not 0. Of course it's not 0. What is the velocity here? And this is initial velocity. You may say that there is no difference in the work. So find the potential energy is m times g, 9.81, times height, which is r. And then this potential energy becomes 1/2 mv squared, and v is this v, and I can find it. No, that's wrong. That is wrong. Because the acceleration due to gravity is no longer 9.81. It is not a constant now. Then why do we say it is a constant for this case? Because this height is small compared with the radius of the Earth. So this height may be, this point may be on top of a high building. But the height of the building can never be as big as the radius of the Earth. Under such conditions, the acceleration due to gravity is still 9.81. It's a constant. Because this height is so small compared with the radius of the Earth. But now, this is the radius of the Earth, then it is not constant. How do we show the acceleration is not a constant? Okay, we do this way. The force of the mass is due to the attraction between the Earth and the mass. So this force is given by the Newton's gravitational, universal gravitation. So the force on M is a constant times the product of the two masses. one mass is the mass of Earth, another mass is the mass of my body. Maybe it's a football, maybe it's a tennis ball, whatever. And then the distance, yeah, square. This is the formula. The distance, what is distance r? The distance, the r is the distance between ME and M. So ME is such a big. How do you measure the distance? You measure the distance between the center of the Earth and your mass. So this distance is from here to here. Okay. But force, this is a universal gravitation formula. But force is also mass times acceleration. So let's consider this mass, the mass times the acceleration of this mass. So this mass is m, therefore force is ma. So what is this A? A is this. A is this. So my acceleration is k me r squared. Now you see A depends on r squared. What is r? R is the distance. R is the distance between this point and this point. But this one is dropping. So the r is changing. Because r is changing, A is changing. Therefore, A is no longer a constant. It is a constant when it's very close to the ground. So, it is a constant when the r is capital R. When small r is capital R, A is 9.81. So, for r equals capital R, A is 9.81, right? You agree? When small r, when this r is this r, so when the mass is near the ground, A is 9.81. Therefore, I can write 9.81 is equal to K E M divided by capital R squared. Huh? Understand? Therefore, K E mass is 9.81 times capital R squared. So this is no longer true. This is for the mass is very close to the ground. But now my mass is very high up the ground, so I need to use this. So this is A, and A is this, right? But then using this relation for R, small r equals capital R, A is this, I have this, therefore KE is this. So I can replace this. What am I doing? Okay. A is okay. I want this KEME. A is this. A is KME over R squared. But KME is 9.81 capital R squared. So that is KME divided by R squared. So I have this relation. What is small r? Small r is the distance between M and the center. So when it drops a distance s, when the mass is here, the small r is the distance from here to here. The distance from here to here is r plus r. This is 2r minus s. So I have 2r minus s bracket square. Do you follow everything up to this step? So I leave this for you to follow. Okay. So next, I use this v dv by ds is equal to this to continue to find my final velocity here. So I need to erase something here. Let's erase here. I need a diagram here, so I erase here. Sorry, I don't have a large blackboard or whiteboard, so I have to keep erasing something. Okay. So I write this, V dv by ds is equal to 981 capital R squared. So 2r minus s squared. Now I start from this, and I want to find the final velocity. Then calculus follows. I need calculus. Okay. So let's erase this. Consider this as a ratio. So I multiply ds here, multiply ds here. So just like the first example, integrate the left side, integrate the right hand side. So left side is v squared over 2. So right hand side well, I have to erase this. I have to erase this, yeah, okay. How do I do this now? Oops. R is a constant, so R squared capital R is a constant. I can move the capital R squared in front of the integration sign. So how do I do this now? Use substitution. Let u equals 2r minus s. Then du by ds is equal to -1, right? us is -1. Or ds is equal to -du. Then this becomes what? 9.81 r square, no, r square, and ds is -du, so I have -du to r, 2r minus s is u, therefore it's u squared. Then I move the negative in front. And I write u -2 du. Follow? Move the negative sign in front here. And write this as negative power. Then I can use power rule to integrate this. Okay. I need to erase it. No, I missed the left-hand side. What is this? The left-hand side. Okay. Okay. Oh, okay. So left side is this. Okay. Yeah. Left side is this. V square over 2. Yeah, left side is it. So this is my left side. So this. So integrate this. Then I have this becomes -1, and I divide by -1, right? And then plus a constant. All right. Do you follow this? The integration of this is this, because you add 1 to this, it becomes -1. And you divide by -1. This is called a power rule, right? So this. And integration constant. Now the negative here and negative here makes it positive. I can write u here. Okay. What is u? U is 2r minus s. So I can replace u by 2r minus s. Now I want to see now. Remember, s is the distance you drop it. Yeah, the mass drops. S is the distance it drops. at the very beginning, the distance drop is 0. So when the distance drop is 0, the velocity is 0. Therefore, c is 0. Okay? Let's see now. When the s is, let's see this. C, okay. Oh, I was wrong. C is not 0. When s is 0, v is 0, but this is not 0. So I have 0. When s is 0, this v is 0, so c is negative that. Therefore, I put this c back into here, so v squared over 2 is equal to c is negative that, so it's negative. Okay, that is what I have. I need to erase something here now. So this is my, after integration, I found the integration constant, and this is my relation between v and s. I want to find the final velocity. The final velocity is when s is dropped, the mass drops through a distance of capital R. So when s is r, the mass is hitting the ground. And I want to find this. So v final is when s is capital R. That means the ball is on the ground, so 2r minus r. And this is 9.81. Look here, r squared divided by r is r, so it's divided by 2r here. Okay, so this is 9.81 r squared. 2r minus r is just r, so (2r minus r is r). R and r squared cancel, so I have 9.81 r. Just r, you cancel that, and I minus 9.81 r over 2. So this minus r is, no, this minus this is 9.81 r over 2. So this is my answer for the final velocity. So if I know the radius of the Earth, I can find the final velocity. So let's do that. I go to the Google and find the radius of Earth. What is the radius of Earth? Okay. So from Google I searched the radius of Earth is 6378 kilometers. Or you can write, change this to meter. Put this number into R and find VF. Now I'm not going to show you each step. Please use the calculator to find it. Then the result is meter per second. This is the velocity. And this, if you use conversion between meter and miles, this is roughly equal to 5 miles per second. So this is a very large number. Yeah. So it's very fast. The ball hits the ground with a velocity of 5 miles per second. Yeah. Of course, this is a theoretical calculation. In practice, there is air surrounding the Earth, and when a mass goes through the air with high velocity, there is friction. And so the energy will be dissipated because of the friction. So this is just an ideal answer. So that's all for today's lesson. Yeah, if you copy this down, then you can follow this step by step. If you have any questions, actually you can send me some message to ask me, and I will do my best to answer your question. So that's all for today. Thank you for watching. Bye-bye.